Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video explains what critical R values are and how to use them. Let's get started. In the previous mini-lecture, we learned about the linear correlation coefficient as an objective means to assess the strength of a linear correlation between two variables. But how strong is strong enough for us to assume that a linear correlation really exists? Looking at how close a number is to 1 or -1 is kind of subjective, and in many respects it's kind of like looking at a histogram and trying to figure out from its shape whether the underlying data are normally distributed. But the more objective means of assessing normality is with a normal quantile plot. Well, here we have a similar situation when assessing correlation, and the equivalent of the normal quantile plot for correlation is the critical R value. Essentially, we have to calculate the R value from our data set, and then we compare that with the critical R value. Now, we make this comparison because the critical R values mark the boundaries between regions of correlation and regions of no correlation. Every data set has associated with it two critical values of R. One is positive and one is negative, and those values are determined by your sample size. So supposing we have a number line here that goes from -1 to 1. So this number line will contain all the possible values for R. Remember, R can't be greater than 1 or less than -1. We have two critical values, one that's positive and one that's negative, and those values will be located somewhere on that number line between 1 and -1. Now, the critical values form boundaries between regions of acceptance and non-acceptance. Non-acceptance means we don't accept the idea that a correlation exists between the two variables in our data set because the association between those variables just isn't strong enough. So if your R value lies in this region here between the two critical R values, then that means we're going to reject the idea that our variables are correlated because there's not a strong enough association between the two variables in our data set. So if your R value from your data set is inside that region of non-acceptance, then your two variables are not correlated. However, if your R variable that you obtain from your data is outside that region, on either the negative side or the positive side, then the two variables in your data set are correlated. You'll notice that the author of your textbook, who also wrote the assignment problems in my math lab, talks about positive and negative tails. He's referring to probability distributions, which aren't introduced until much later, so I was more than a little surprised to see that. That said, it's easy to figure out what he's talking about. Just think of a positive tail region as this region of acceptance on the positive side of your number line, and here where the R value from your data is greater than your positive critical R value. Likewise, you can think of a negative tail region as this region of acceptance on the left, where the R value from your data is less than the negative critical R value. So there's the positive tail region on the right, the negative tail region on the left. Let's look at an example to illustrate this concept of critical R values. Suppose we have a researcher monitoring the growth of bacteria in a Petri dish. This researcher obtains the data listed in the table here by counting each day the number of bacteria in the Petri dish. So on day 1, we have 30 bacteria. On day 2, we have 45, so on and so forth. The linear correlation coefficient R for these data is 0.8999. Now we're asked, what are the critical values of R, and what can you conclude about a linear correlation? Well, you typically find critical values of R from a table that lists different sample sizes with the associated critical R values. Now, those of you working assignments in my math lab will see next to the problem statement a little book icon like you see on the screen here. When you click on that icon, a table like this one appears. This is your table of critical R values. Just find the size of your sample in the table, and the value right next to it is your positive critical R value. Don't forget you have two critical R values, so to get the negative one, just add a negative sign. Now, we're going to use the table to find our critical R values for this example problem. So first, we look at the left side of the table to find the number of pairs of data. What's our sample size? Well, our sample size is 7, because here, see, we have 7 pairs of data, okay? And so 7 in the table is located right here. Then we just look across the same row on the other side of the table, and there's our critical R value, 0.754. But remember, we have 2 critical values of R. So one is positive and one is negative. So to indicate that, we could list them each separately or just use a plus or minus sign like you see here. Okay, that answers our first question, but what about the second question? Well, now that we know what our critical R values are, we can compare those with the R value we get from our data. I'm a visual learner, so I find it helpful to draw a number line with my critical R values in place. Then all I need to do is add in the R value from the data set. The R value from our data here is 0.8999, which would place it here on the number line. What region are we in? Well, we're in the region of positive correlation, which is the region of acceptance on the positive side. Therefore, we can conclude there is sufficient evidence to support a claim of linear correlation between the number of days and the number of bacteria. That's all there is to it. If the R value from our data was in the middle region, then we would conclude that we don't have sufficient evidence to support a claim of linear correlation. And if our data generated R value was in the region on the left, we conclude as we just did. The only difference is that the correlation would be negative instead of positive. And that's really all there is to it. And that brings us to the end of this mini lecture. I hope you found it helpful. If you'd like more practice with other problems, like the example problem we just worked, then check out the next mini lecture. Otherwise, feel free to skip it. And as always, you can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.